Okay, let's unpack this. We talk about AI constantly, right? It's in the news, it's on our phones, it's writing our emails. But usually, we talk about the output, the funny chatbot responses, the translations, or the occasional hallucination where it just invents a court case. But
Yeah.
today we are going under the hood. And I don't mean just popping the hood to look. We are taking the engine apart.
We are stripping it down to the bolts.
Exactly. We aren't just talking about robots talking.
Yeah.
We are looking at the specific architecture, the literal layers that allow a machine to look at a jumble of text and actually parse meaning from it.
It's a fascinating topic because it grounds all the hype in, reality. To guide us, we're doing a deep dive into a very specific, rigorous text, Chapter 15 of Deep Learning for Natural Language Processing by Kung-Yun Cho.
And I'm really glad we have this specific source because otherwise this topic gets overwhelming fast. This isn't some fluff piece. This is a textbook chapter that moves from the basic building blocks all the way to those complex translation systems we use every day.
Right. And the mission here is really to demystify the term deep learning. It sounds magical, almost sci-fi, doesn't it? Like the machine is pondering existence in a dark room. But Cho makes it very clear right from the intro. Deep learning is actually just a subset of statistical machine learning. It's math, not magic.
So let's start with that definition. What makes it deep? Is it because it, thinks deep thoughts, or is it deep like a deep dish pizza?
Closer to the pizza, actually. Deep in this context refers to the structure. It refers to a stack of many layers, specifically nonlinear layers.
Okay, layers. I usually hear people compare this to a neural network, like a brain. But in this text, it feels more like a filtration system.
That's a better way to visualize it. The most basic unit Cho describes is the fully connected layer. Imagine you have an input, say, a set of numbers representing a word. In a fully connected layer, every single number in that input connects to every single output node.
That sounds chaotic.
It is dense. You take that input, you multiply it by a weight matrix, which is what the machine learns. You add a bias term, and then, and this is the absolute key, you apply a nonlinear function, usually something like a tan or a sigmoid function.
Okay, I have to stop you there. I barely passed calculus. Why the nonlinear function? Why can't we just add up the weights and biases and call it a day? Why do we need to make it curvy?
Because the world isn't linear. Think of it this way. If you just stacked a bunch of linear layers, just adding and multiplying, you could mathematically collapse them all down into just one single linear layer. You wouldn't gain any complexity.
So it would just be a straight line.
Exactly. Imagine I gave you a piece of paper with glue dots and red dots scattered all over it in a swirl pattern, and I told you to separate them with a single straight line.
I couldn't do it. I'd need to draw a circle or like a squiggly line to separate them.
Precisely. That squiggly line is the nonlinearity. By applying these functions, tan or sigmoid, after every layer, you allow the model to learn complex, curvy boundaries between data. It lets the machine capture nuance.
That makes sense. So the nonlinearity is what lets it understand that bank means money sometimes and a river other times, depending on the context. It's not a straight rule.
Correct. So that's your basic layer. But then the text takes a turn that I think usually trips people up. Cho starts talking about convolutional layers, or CNNs.
Yeah, I flagged this. Usually when I hear convolution or CNNs, I think of computer vision. Self-driving cars, seeing stop signs, or Facebook finding my face in a photo. What is an image processor doing in a text chapter?
That is the common association. In an image, a convolution filter slides over the pixels looking for spatial features, edges, curves, corners. But Cho explains that in text, a convolutional layer acts as an n-gram detector.
An n-gram detector. Break that down.
An n-gram is just a sequence of n items. A 2-gram is 2 words. A 3-gram is 3 words. So imagine a filter sliding over a sentence instead of an image. It's not looking for an edge, it's looking for a specific phrase or pattern of words.
Give me an example.
Let's say the filter is trained to find the concept of a predator hunting. It might be looking for the sequence chases a lion.
Okay. And this filter slides across the sentence.
Yes. And this brings us to a concept called translation invariance.
Which means what? Doesn't matter what language it's in.
No, translation here means movement in space. It means it doesn't matter where in the sentence the phrase chases a lion appears. It could be at the very beginning or at the end.
The filter lights up either way.
Exactly. It detects the pattern regardless of its position. And then usually this is followed by something called a pooling layer.
Which sounds like a swimming pool, but I assume it's not.
Unfortunately not. Pooling is about summarizing. It essentially looks at the output of that filter and says, okay, did we see the chases a lion pattern anywhere in this chunk of text? It reduces the dimensionality.
So it's like a manager reading a report and just checking a box. Yes, predator concept present. It doesn't care exactly where it was, just that it happened.
That's a great way to put it. It makes the system robust to small shifts.
Okay, so CNNs handle patterns and phrases. But text isn't just a bag of phrases, it's a sequence. Order matters. And more importantly, sentences aren't all the same length.
Right.
If I'm a computer, I want fixed inputs, a nice, neat grid. But a sentence can be 3 words or 300 words. That seems like a nightmare for a standard network.
That is the perfect transition to the recurrent layer, or RNN. This is the heavy lifter of NLP. Unlike CNNs, which look at local chunks, RNNs are designed specifically for sequences.
How do they handle the fact that I don't know when I'm going to stop talking?
They process the text one symbol or one word at a time. But here's the magic trick. They have a hidden state.
The hidden state.
Think of the hidden state as a memory backpack. At each time step, the model looks at the new word coming in, but it also looks inside its backpack to see what it's already carrying from the previous words.
So if the sentence is, the cat sat on the mat, when it gets to Matt, it's not just seeing Matt, it's seeing Matt plus the memory of the cat sat on the...
Exactly. It updates this memory vector at every single step. It takes the old memory, mixes it with the new word, and creates a new memory. Theoretically, by the time it gets to the end, that final hidden state should contain the meaning of the entire sentence.
Theoretically. I hear a tone in your voice.
Well, there's a problem. Cho discusses this extensively. Imagine playing the game Telephone, but you have to whisper a story to yourself 50 times in a row, adding a word each time.
I forget the beginning by the time I got to the end.
Precisely. In the field, we call this the vanishing gradient problem.
Vanishing gradient. Okay, that sounds dramatic.
It is for the math. In a simple RNN, as you process a long sequence, the signals from the beginning of the sentence get weaker and weaker. You're multiplying matrices over and over again. If you multiply a fraction by a fraction by a fraction, what happens?
It gets tiny. It approaches 0.
Right. So the information vanishes. The model might get to the verb at the end of a long paragraph and forget who the subject was at the start. It has amnesia.
So we have a brain that can't remember anything longer than a tweet, and seems useless for reading a book. How do we fix it?
The solution Cho outlines is one of the most important developments in the history of NLP. The gated recurrent unit, or GRU, and the LSTM, long short-term memory.
On short-term memory. That's a mouthful.
It is, but the key word is gate.
Like a garden gate.
Like a security gate with a bouncer. In a simple RNN, the model blindly overwrites its memory at every step. It just creates a new mix. But LSTMs and GRUs have gates that make active decisions. They decide what to keep and what to throw away.
So the bouncer looks at the new word and says, that's not important, don't let it change the memory much. But then it sees not and says, whoa, that's crucial, let that in.
That is a great analogy. An LSTM has a forget gate to dump irrelevant info and an input gate to catch important new info. But there is a technical detail Cho highlights that is absolutely critical here. It's called additive updates.
Additive updates, why does that matter?
Remember how we said multiplying over and over makes the signal vanish?
Yeah, the fraction's getting smaller.
Well, LSTMs allow information to be added to the memory stream rather than just multiplied into it.
Oh, so it's like a shortcut.
Exactly. It creates a gradient superhighway. This allows a detected feature, say, the fact that the subject is female, to be maintained unchanged over a long duration. It can bypass all the processing in the middle and just ride that highway until it's needed again.
So it solves the amnesia. It can hold on to she for 10 sentences until it hits the verb her.
Correct.
Okay, so we've got the architecture, we have these fancy layers with gates and highways, but we need to talk about what we're actually feeding these layers, because computers don't read words, they read numbers.
Right.
So how do we turn cat into a number? My instinct would be just to make a list. Aardvark is 1, apple is 2, zebra is 50,000.
You could do that, but that creates a massive problem. In math, 50,000 is much bigger than 1. Does that mean a zebra is more than an aardvark?
No, they're just animals.
Exactly. The numbers imply a relationship that doesn't exist. So for a long time, the field used something called one-hot vectors.
One hot. Sounds like a boy band.
It's less exciting. Imagine a list of every single word in the English language. Let's say there are 100,000 words. A one-hot vector for the word cat is a list of 100,000 zeros with a single 1 at the spot for cat.
That seems incredibly wasteful. You have this massive string of zeros just to say cat.
It is sparse and inefficient, but the bigger problem is that it captures zero meaning. In a one-hot representation, the mathematical distance between dog and cat is exactly the same as the distance between dog and microwave.
So the computer has no idea that dogs and cats are related.
None. This is where deep learning changed everything with distributed representations, or word vectors. Instead of a sparse list of zeros, we compress that information into a smaller, dense vector of real numbers, maybe 300 numbers. And the machine learns these numbers
How does it learn them?
by using the distributional hypothesis.
Which is,
It's the idea that you shall be known by the company you keep.
okay. So if dog hangs out with bark, furry, and pet, and cat hangs out with meow, furry, and pet.
The model notices that overlap. It adjusts the numbers, the weights, so that the vector for dog and the vector for cat end up mathematically close to each other in space.
So if I visualize this, dog and cat would be floating right next to each other, and microwave would be way over in the kitchen corner.
Exactly. But here is where Cho's chapter gives us a massive aha moment. These vectors aren't static. They change based on what the model is trying to achieve.
Meaning the definition of a word depends on the job the robot is doing.
Yes. Cho gives a fantastic example comparing an English to French translation model versus an English to German model. They looked at the vector for the English word earned.
Earned, like I earned $5.
Right. In the English-French model, they looked at the nearest neighbors to earned. Guess what they were?
I assume words like worked, salary, job.
You'd think so. But the closest neighbor was actually one.
One, like a lottery. But earned implies effort. One is luck. Those are opposites in my head.
To a human, yes. But think about the task. The model is translating to French. In French, the word gagner means to win a game, and D to earn money.
Oh, so both English words map to the same French word.
Exactly. So to the model, won and earned are functionally synonyms. They produce the same output, so their vectors get pushed together.
It is wild.
But wait, in the English to German model, it was different. German distinguishes between verdienen to earn and gewinnen to win.
So in the German model, earned and won were far apart.
Yes, in that model, earn was distinct from won.
That blows my mind a little. The machine doesn't know what earned means. It just knows its utility for the specific language it's targeting.
It optimizes for the objective function, not for philosophical truth.
Okay, so we have word vectors concepts turned into numbers, and we have RNN's memory backpacks. Now we combine them to do the holy grail of NLP, machine translation.
This brings us to the encoder-decoder framework.
Walk me through this.
It's a two-part system. The encoder reads the source sentence, say in English, one word at a time. It uses that RNN architecture. At the very end, it produces a single context vector, often called C.
And that vector C is supposed to be the summary of the whole sentence?
Yes. Then the decoder takes that single vector C and starts generating the translated sentence, say in French, one word at a time.
Wait, pause. We just talked about the backpack problem, the telephone game. If I have a sentence that's 50 words long and I crunch it all down into one single vector, aren't we losing a ton of detail?
You hit the nail on the head. That is the bottleneck. You are asking the model to compress War and Peace into a single sticky note and then translate it perfectly. It's incredibly inefficient.
So the translation ends up sounding generic or just wrong. How do we fix the bottleneck?
We introduce the attention mechanism. This is the climax of the chapter and really the climax of modern NLP.
I love the name attention because for once it sounds like what it actually is.
It does. Here's the shift. Instead of forcing the decoder to rely on just that one final context vector, the attention mechanism allows the decoder to look at all the hidden states from the encoder.
All of them. Like every single step of the original sentence.
Every single word.
But isn't that information overload? If I'm translating the last word, I don't need to know the first word.
That's where the attention comes in. At every step of generating the translation, the model assigns weights or scores to different parts of the input sentence. It decides what is relevant right now.
Okay, give me a visual.
Imagine a spotlight. The model is trying to write the French sentence. It's about to write the word European.
Okay.
Before it writes it, the spotlight scans the original English sentence. It shines very brightly on the word European, maybe dimly on union, and leaves the rest in the dark.
So it focuses on the source word that matches the target word it's trying to build.
Exactly. And then for the next word, say économique, the spotlight moves and focuses on economic.
That makes so much sense. It's not trying to remember the whole sentence at once. It's looking back at the source text word by word as it writes.
It's called soft alignment. It learns which English words align with which French words dynamically. And this completely removed the bottleneck. The quality of translation just skyrocketed because the model didn't need to have a perfect memory, it just needed to know where to look.
It feels like that was the moment deep learning really grew up. It stopped trying to just memorize and started trying to, well, pay attention.
It did. And once you have that, Cho points out that you can start conquering new frontiers.
Yeah, the chapter ends with some really cool advanced stuff. One was multilingual modeling.
This is fascinating. It's about using multiple languages to improve understanding. Cho discusses using a pivot language.
I don't know that word.
Let's say you want to translate English to Kazakh, but you don't have many books translated between those two. But you have a lot of English to Russian and Russian to Kazakh.
You can triangulate.
Exactly.
Yeah.
But it goes deeper. Remember our win versus earn example? If you feed the model multiple languages at once, it enriches the word vectors. If win and earn both translate to the French gauner, the model learns they are related. If you add Spanish, where they might be different, it adds another layer of nuance. The model starts to build a more universal representation of meaning.
That is incredibly cool. It's like learning a second language helps you understand your own language better.
It really does.
The other frontier that caught my eye was larger context modeling, because everything we've talked about so far is mostly happening inside one sentence.
Correct. And that's a huge limitation. Human communication isn't just disconnected sentences.
Right. If I say, he was fired, you have no idea who he is unless you heard the previous sentence.
Exactly. This is the problem of intersentence context. The text mentions a great example involving the BBC and Jeremy Clarkson.
The car guy.
The car guy. Imagine a document. Paragraph 1 talks about Jeremy Clarkson getting into a scuffle with the producer. Paragraph 2 starts with, he was fired by the BBC. If you ask the model who was fired, and it only looks at the second sentence, it fails. It just sees he. It doesn't know who he is.
It needs to look back at the previous paragraph to resolve the pronoun.
Exactly. Larger context modeling aims to model the probability of a whole document rather than just independent sentences. This is essential for answering questions where the answer isn't in the query itself, but in the supporting text.
It's the difference between reading a sentence and reading a story.
That is the ultimate goal.
You know, looking back at this chapter, it's quite a journey. We started with simple math separating dots with lines. We saw how CNNs can act as pattern detectors for phrases. We watched RNNs struggle with amnesia until the LSTM showed up with their bouncers in memory highways.
And then the shift to word vectors, where meaning is defined by usage. And finally, the attention mechanism, which gave the machine a spotlight.
It's amazing how we've moved from data sparsity, that old problem of just not having enough examples, to this world where the model can generalize. The text used the example, chases a lion.
Right. In the old days, if the computer had never seen the phrase chases a lion, it would think that sentence was impossible. Zero probability. But with deep learning, if it knows chases a cat and chases a dog, and it knows lion is mathematically close to cat and dog,
It can guess that chases a lion is a valid sentence, even if it's never seen it before,
it creates possibility out of patterns.
which is fantastic. But I want to leave our listeners with that thought about the word vectors again. The won versus earned thing is going to keep me up at night.
It's the most provocative part of the chapter for me as well.
Because if machines learn meaning based strictly on the task they are assigned, like how earned means won if you're translating to French but not if you're translating to German, makes you wonder, does a machine ever truly understand a word?
Or does it only understand the utility of a word?
Exactly. It's like a student who learns the answers to pass the test but doesn't actually know the subject.
We're building systems that are incredibly useful mirrors of the tasks we give them, but we have to remember, they are mirrors of the task, not necessarily mirrors of reality.
And what happens when we give it a task we don't fully understand ourselves? That's something to chew on. Thanks for diving deep with us today.
Always a pleasure.